Hey everyone, this is Mrs. Sherburne and I would like to review the iron wire demonstration with you. So you can tell that I have the iron wire set up right here, and here I have a magnet. Iron's magnetic, and I have a weight hanging in the center, and I'm going to have electricity that's flowing through this circuit. But I don't want to just take my extension cord that I've altered and plug it right into the outlet. Instead, because that would be a full 110 volts. Instead, I just got this variac, and that allows me to vary the voltage. So I'm going to start off with 0 voltage and slowly crank it up. Some things that I want you to watch for as the electricity increases is incandescence. So the iron wire is going to exhibit a property that it's going to heat up so much that it's going to give off light. That's known as incandescence. Will also get it hot enough that it will reach the Curie temperature. The Curie temperature is the temperature that a ferrous material, iron, loses its magnetism. And that happens at 770 Celsius. And then the last thing that I really want you to notice is once I get it red hot and I turn off the electricity, you're going to be able to see the iron change crystalline structure. So remember, metals exhibit crystalline structure, and there's different types of crystalline shape that they can take. You know that when blacksmiths want to make a sword or horseshoes or something out of iron, they heat it up so that it's more workable. And what that means is, on a crystalline level, is that iron right now is exhibiting something that's known as the body-centered cubic structure. I have a red ball or sphere that's in the center. That means nothing. I just put it red so that you can see it easier. All of these styrofoam balls are supposed to be iron atoms. So there's 4 at the top, 1 in the center, body-centered cubic, and 4 on the bottom. And it looks the same from all angles. But when I heat iron above 912 Celsius, it changes from body-centered cubic to face-centered cubic. And that looks a little more like this, so that you have an atom at the face of the cube. It cuts down on the space that's in between the atoms, and you might think that if there is more space, more gappiness, you would think, well, that should make it more workable. But that's not actually what happens. And so if you look at this demonstration, if the atoms are spaced apart, think about ruts in a road and like the tires going across it. If I have the ruts in the road that are really close together, I can have the tires go and slip past each other, slip past the ruts a lot easier than if I have gaps in here. This is much more workable if the atoms are more closely packed and can slide past each other. So that's why we want iron to get hotter than 912 Celsius, so that it changes from a crystalline structure that's more gappy to one that's more closely packed. When I turn off the electricity, you're actually going to notice, so I want you to really pay attention for when this happens. The wire is also going to start sagging down. It's going to sag because as I give that more heat and more energy, it's going to experience thermal conductivity. So thermal expansion. The wire is going to start sagging, sagging, sagging. That's what the weight's there to help stretch it out as it heats up. But when I turn off the electricity, it's going to shrink back together. But it's not going to be an even shrink. You're going to see a dip. So it's going to go from being down like this, and it's going to go up a little bit, dip back down, and then continuing going back up as it cools. It's returning to the body-centered cubic structure, and you get to see something that is evidence for that. So heat it up, I get to face-centered cubic, let it cool back down to room temperature, and I'm back to body-centered cubic. So let's actually see what happens. You might want to get a little bit closer And I'm gonna turn off the lights so that you can see this incandescence a little bit better. Hold the camera steady so that you can really see the wire starting to expand. Hopefully you can see that weight going down. It definitely is expanding. Let's turn off both lights. Oh, it's starting. And there's a couple spots that are starting. Can you see it on the camera, or do you want the lights back on?
I can see it on the camera.
Okay, I want you to focus in on the magnet if you can. And you don't have to zoom in, but really watch this dark spot right here. And you might call that a heat sink because it's not getting as hot as the rest of the wire. The weight's acting as a heat sink also. Okay, I'm up to 75 volts. Okay, watch the magnet. 770 Celsius, and we're at the Curie temperature. If I turn the lights back on, can we still see it glowing? Oh, starting to shake a little bit. You can still see it glowing, can't you? Oh, okay, so 770. I'm going to turn it up a little bit more. Okay, we are at 95 volts right now. All right, I'm going to shut it off. Watch the weight. Did you see that dip? It happened pretty quick. We might have to back the video up so that we can see it a little bit better. Don't pause it quite yet. So one last thing that I want to do, and iron, aluminum, metals have a pretty low specific heat. When you're talking about something with a low specific heat, that means it doesn't take a lot of energy to heat up, and it also doesn't take very much energy for it to cool down. Like, it cools down quick, but it also heats up quick. Most metals have a low specific heat. A material that would have a high specific heat might be something like water. If you live near water, you know that it takes a long time, it takes a lot of energy to heat up water. And it also takes a long time for water to cool down. Water has a high specific heat. Okay, I think I should be... Okay, it's cooled down enough that I can actually touch it. And I'm gonna do some voodoo. I'm gonna make some voodoo spots on here, and I want you to see if you can actually see the spots that I do my voodoo magic on. And I'm just picking some spots. Okay, this is voodoo magic here. And we're gonna turn it back on. All right, you can probably see it dipping back down. Can we get the light shut off back here? And see if we can see my voodoo spots. Maybe turn the front lights on. Oh yeah, there they are. Those are my voodoo spots. So what's going on there? Why can you see the incandescence, the wire glow so much better? I'm gonna continue turning up the voltage. So the rest of the wire is gonna start glowing. But I did something there. Think about what that might be. And I want to turn it back up a little hotter and see if, oh, and I did put my magnet on there. So we're not going to be able to see the magnet drop off at the Curie temperature. I'm at 90 volts. All right, let's get a close-up, a little bit of the weight, and hold it very steady because I'm about to turn the electricity off. We'll go on 3, 2, 1. Dip, and then continues going back up. So that's the solid state phase change from FCC being more workable back to BCC. Thank you so much. I hope you enjoyed the iron wire demo.